All right, you're good to go.
All right, welcome everyone. I'm really excited today to present Sriram and the work he's been doing. I've known him for a few years now, where he was working with Nidhi at Borealis AI. And recently he's been doing some really cool stuff with mean field reinforcement learning. Now, I particularly like that his long-term goals are looking at how do we get multi-agent RL into the real world. And I think many of you will find it interesting that he's particularly interested in conservation problems. So thinking about forest fires. So again, thinking about how reinforcement learning is this awesome tool and it can be used for real world things, not just video games. So with that, I'll hand it over to Sriram, where he'll talk about his work in video games.
Thank you, Matt. Can you see my screen?
Yep, you're good.
Okay, and I assume you all can hear me as well. Okay, yeah. So thank you all for having me. Welcome to my talk on recent advances in mean field reinforcement learning methods. An acknowledgement to all the collaborators that I have got help from: Mark Crowley, Matthew Taylor, Nidhi Hegde, and Pascal Poupart. So let's dive straight in. So let me just start the talk by giving a very quick introduction to stochastic games. I just want to make this talk be self-contained. So I guess MDPs, most of you would be familiar with that. We have a tuple which contains the state space, the action space, the reward function, the transition function, and the discount factor. The state space, the state denotes what the agent sees. The action is what the agent can do. The reward is the signal that the agent gets based on if the action was good or bad. And then there's a transition function which gives the probability of moving to another state based on the state that the agent currently is and the action the agent did. Now, the stochastic game can be looked at as an n-agent MDP. So it can just be seen as a generalization of a single agent MDP to n agents. And now we have a tuple where here we have n, which is the number of agents. And then we have s again, which is the shared state space. Shared amongst all the n agents. And then the action space here will include all the agents' actions. So here we have n agents. So the way I've represented it here is A1 cross A2 cross and so on to AN. The reward function for agent J will also be dependent on all the other agents' actions. So it will be R of S and again A1 to AN. So it includes all the agents' actions. The transition function will also include all the agents' actions. And again, we have the discount factor similar to MDP. So again, this talk is going to be on multi-agent reinforcement learning. Some of you may be familiar with that already. The multi-agent reinforcement learning is an active area of research. It's had lots of successes in the last decade, especially mostly in video games. Matt was just talking about that. We have had successes in two-player games like chess and shuttle and so on. And we've also had some real-world successes. Multi-agent reinforcement learning has been used in robotic navigation, coordination, etc., in real-world industrial settings. The main challenge with multi-agent reinforcement learning for many large real-world environments is that the algorithms typically the multi-agent algorithms are exponential in the number of agents. So here I have a figure which captures this interaction. So if you have a finite number of agents, then every agent interacts with every other agent in this environment. So for example, if we have the standard Q function, the Q function for an MDP would be QSA, where the parameters would just be the state and action. But for the multi-agent space, the Q function will depend on the action of all the agents. So if there are two agents, it will be QS A1, A2, where the A1 is the action of agent 1 and A2 is the action of agent 2. So you can see that now the parameter space is exponentially increased. For every state action pair, you have an additional action, which is the action of the other agent that just got introduced. So going on like this, it is easy to see that the problem is exponentially complex as we add more and more agents. The problem becomes exponentially more and more harder to solve. And therefore, at some stage, our modern computing systems are going to say that it's not tractable anymore to solve the problem. So if you consider some real world environments with lots of agents, for example, stock trading or like grid optimization for supplying power for a large city, you have large number of agents, and typical multi-agent RL algorithms may not be tractable. There is a lot of recent research in this area. there has been research on how to make multi-agent RL algorithms tractable. One proposed solution has been just using independent agents. Independent agents just assume that all the other agents are just part of the state space. This approach, even though it does not intuitively seem to do well, in some cases it has done well, and in some other cases it has failed. There is still there needs to be some research in that area. There's also been some proposed approaches in parameter sharing and similar kind of approaches. But the topic that I'm going to deal with today is making multi-agent algorithms tractable using mean field methods. So the mean field approach is what I'm going to focus on in this talk. So in the mean field methods, the critical there are some critical assumptions, and then there are some restrictions that we want the environment to have before the mean field approaches can be even applied. So the first thing to notice is that in a large environment with many agents, probably the individual agent's impact is limited. Let's take an example of autonomous driving, where you have an autonomous vehicle which wants to navigate from, say, point A to point B. And here, when it's trying to navigate from point A to point B, the vehicle is not particularly interested or concerned about another vehicle in this environment, another single vehicle in this environment. Rather, it's worried about global parameters like, say, traffic flow or traffic density in a particular route, so that it can reroute itself. This kind of observation makes us come to the conclusion that the opponents or the other agents in the environment can possibly be aggregated, and this aggregated measure can be used as the metric to which agents formulate best responses, rather than formulating best responses to each individual agents. There is an important assumption for all mean field methods. We need to assume that the agents are homogeneous and indistinguishable. So agents have some similarity in their objectives and their reward functions and so on. And another assumption is that agents maintain weak interactions only through the mean field. So this again comes back from the example that I gave you before. Agents don't give best responses to other particular agents. Rather, they only give best responses to the mean field, because that's the only tractable option that's possible. These mean field methods effectively decompose this entire large environment with many agents in it into a 2-agent environment, where the second agent is the virtual mean field. So the virtual mean field captures the essentials of all the interactions across all the agents, and agents typically look to formulate best response strategies to this mean field rather than every other agent in this environment. Okay, so let me now just briefly summarize different types of mean field methods that are there in literature, and the different types of mean field methods that have been applied to reinforcement learning. So there are 3 very popular mean field methods in literature. One is the mean field game model, the second is the mean field control model, and the third is the mean field reinforcement learning model. So let me just give the main points of differences between these. So for both the first 2 models, mean field game and mean field control, the assumption is that the environment has almost infinite number of agents, or infinite number of agents in the limit. And this particular assumption makes some other critical differences between these models and mean field reinforcement learning, where mean field reinforcement learning just assumes that the number of agents are large, but they could possibly be finite. It's fine if the number of agents are finite. The underlying model for the mean field game is the mean field game model. So the mean field game model actually transforms the underlying game into a different kind of a game, where the dependence is only on the mean field. So if we go back here, when I talked about stochastic games, I talked about all these interactions for all these agents with all the different agents, all the agent actions. So if you see, the reward function depends on the state as well as all the n agent actions. But for the mean field game model, the dependence will only be on the mean field. So it will just be S bar, A bar. So just on the mean field. And the transition function will also only depend on the mean field. And if you formulate a Q function or a value function, correspondingly, the dependence is only on the mean field straight away. But for the mean field reinforcement learning, remember that the underlying model is still a stochastic game. So we are still dealing with a stochastic game. Even though there are a large number of agents, the underlying model is still a stochastic game, and all the interactions are a stochastic game interaction. For the mean field control model, there is a small difference. It is very similar to mean field game. except that there is an assumption of a centralized controller, which is controlling everything. So here the agents are not independent, or the agents are not individual per se. So the agents are not making their own, learning their own policies and taking their own actions. There is a centralized controller which just formulates all the best response strategies and then just passes that on to every agent. So the mean field game can generally works in non-cooperative environments. Non-cooperative does not mean non-collaborative. It just means that all the agents are independent. Mean field control works in just cooperation, pure cooperation, coalition forming environments. And the mean field reinforcement learning is more flexible. It can work in both different kinds of environments. If you're familiar with the stochastic game model, you know that the stochastic game model is a very flexible model. So if you look at the Q function and value function, like I just said, there is an exact dependence on the mean field for both the mean field game and mean field control. But in mean field reinforcement learning, it's more of an approximation. So there is an approximation, and then we formulate an approximation error. And we can show that when the number of agents gets larger and larger, this approximation vanishes, or this approximation error goes to zero. So the solution concept for mean field game is a mean field equilibrium, and for the mean field control is a Pareto optimum, because it's just a cooperative game. Just the model that the solution concept is just a Pareto optimality. And for mean field reinforcement learning is a Nash equilibrium, because it's still a stochastic game. So the rest of this talk is just going to focus on the mean field reinforcement learning. But the reason why I had this slide is because you see the mean field reinforcement learning model is pretty recent. It was just introduced in 2018. But both the other models, mean field game and mean field control, have been existing for quite some time. I think mean field game was introduced in 2007 by Lastry and Lyons. So it's been existing for quite some time. It's possible that some of you are familiar with these models. And I want to emphasize that mean field reinforcement learning is different from them. So if you're already familiar with these models, there could be some misunderstanding or some confusion when I'm talking about different aspects of mean field reinforcement learning. So just want to put it out there that these models are different. And if you have, just keep that in mind. If you are from the other backgrounds, if you're from the mean field game or mean field control background, just keep that in mind that this talk is on mean field reinforcement learning. All right. So let me go into the concept of mean field reinforcement learning a little more. Let me go into more details. So this paper, this field was introduced by a paper from Yang et al. In 2018. This paper from Yang et al. Was released in ICML in 2018, and it's very highly cited. It's even within 2 years, it's got about hundreds of citations. The reason why this is very popular is that this method is more practical, is very practical. It's more practical than the other two methods, arguably. And this paper also introduced the theoretical foundations for mean field reinforcement learning, also some practical algorithms that worked very well. That's why this paper is very popular. Some assumptions that the Yang et al. Paper had were, there were two very critical assumptions. One is that the agents are homogeneous, which means that there's just a single type of agent and all of them are homogeneous. And then the second assumption was that all the agents are fully observable. So this is, again, the assumption is not, it's quite restrictive because you have a large environment, but you still have to assume something about observability, about full observability. Given these assumptions, Yang et al. Showed that the Q function can be factorized into you just using pairwise interactions. So if you look at this equation I have here, you have the multi-agent Q function on the left-hand side, where you have the dependence on all the actions of all the n agents. And then on the right-hand side, you only have the pairwise interaction. So this is just capturing the pairwise interaction between two agents. And then there's a summation across all the agents in the environment. So given these assumptions, you can show that the Q function can be factorized in this way. And further, the Q function can also be approximated with just using the mean field. So instead of all these n different agents, actions involved in the Q function, you can just approximate it using just the mean field action A bar. So Yang et al. Showed these properties, and then they gave a proof of convergence to the Nash Q when you're using the mean field approximation when you're using mean field approximation in practical environments. So I want to just spend a minute or two with this mean field variable, because this particular mean field A bar can trip people up. So if for just to put it clear, just to make it clear, A bar is actually a distribution. So it's not another action, but it's a distribution of actions. So the way it's calculated is for a discrete action setting, and actions are represented as a one-hot encoding. So actions of all the agents in an environment are represented as a one-hot encoding. And then an average of all those one-hot encoding is taken, or not encoding actions are taken to get A bar. So as an example, if you consider an environment with 4 agents, and let's say agent 1 is doing action 2, agent 2 is doing action 1, agent 3 is doing action 4, and agent 4 is doing action 3. Now this mean action for this environment would just be the summation of each of these different components and divided by 4, because you have 4 agents. So it's just 0.25, 0.25, 0.25, 0.25 on the 4 dimensions. So mean field reinforcement learning so far has only been restricted to discrete action spaces. There is not much study done in continuous action spaces. But for the sake of completeness, let me also say that if you have a continuous action space environment, you could do something like you could probably take the density function of the mean field by looking at representing the other agents' actions as a direct delta distribution, and then taking a mean the same way as you do for the discrete space. Okay, so so far I have laid down the groundwork in mean field reinforcement learning, and I'm going to be talking about some particular contributions from our lab, and which I have been involved in. Particularly, I relaxed these 2 important assumptions that I was talking about in the previous slide. The first assumption was that we need all the agents to be homogeneous, and we relaxed that by making MFRL applicable to heterogeneous agents. And this was a paper in Amii last year, and it's titled Multi-Type Mean Field Reinforcement Learning. And then we relaxed the second assumption to make MFRL applicable to environments with partial mean field observation. And this was a paper in this year's Amii, and it's called Partially Observable Mean Field Reinforcement Learning. So the rest of the talk is going to focus on these 2 topics. So far, are there any questions? So hopefully the mean field reinforcement learning model is clear, and hopefully it's clear that this model is different from mean field game or mean field control. Okay, I'm sorry, I'm not tracking the chat. So if you have a question, please unmute and ask. If you've put that on the chat, I will come back to it at the end. Okay, seems like it sounds good. Okay, so now I dive into the first contribution, which is multi-type mean field reinforcement learning. So consider a group of heterogeneous agents in an environment. Like I said before, MFRL cannot be applied directly because MFRL has an assumption that all the agents have to be homogeneous before you can apply the mean field reinforcement learning technique. So, so our idea was that if you have a group of heterogeneous agents, hopefully these heterogeneous agents can be classified into types. And let's say that all these heterogeneous agents can be classified into a finite number of types, a finite number of M types. And then each type can possibly have a different MDP. So they can have a different reward function, they can have a different action space even. Any differences are fine. And then we are actually applying the mean field model within the type rather than across types. So, so here the first assumption has been removed. We don't need all the agents to be homogeneous, and it's not a single type model anymore. We still retain the second assumption for the time being. We'll still retain full observability. Now the Q function, we show that can be factorized using pairwise interaction of types rather than simple pairwise interaction. And then we also show that the Q function can be approximated using types rather than just a simple approximation with a single type. So now, instead of having a single type, we have an approximation over all these M types. So if we have N agents that can be approximated into M types, then the Q function can just be the MTMF Q function, which is different from the mean field Q function. This is the multi-type mean field Q function, can be approximated with these finite number of types in the game mode. Okay. So now I just come to the particular update equations in mean field reinforcement learning. So in mean field reinforcement learning, there were 4 different update equations that happened in sequence. for the learning to take place. The first one was the update of the queue function. So the queue function depends on, like I just mentioned, the queue function depends on the agent's action as well as the mean field action. And this is updated using the Bell-Ben equation. And then the value function for this update comes from just taking an expectation of the queue function. And then once the value function is obtained, the mean field has to also be updated. And this is updated by using the actions of all the agents and then just doing an average based on how I just explained using an example. Once we have all these values, then the Boltzmann policy is updated using the queue functions. So this is the mean field RL update, the second column here. And then for the multi-type mean field RL, the major difference is that wherever there is just a single type, we can just substitute all of that using the multi-type approach. So wherever there was just the A bar, we can substitute all of that using the M types. And empirically, this is simple. Empirically, we can simply make these substitutions and it works and it gives us good results. But the major selling point of our paper is that even theoretically, we can show that all the approximation bounds or the different theoretical properties that Yang et al. Had, all of them also extends to the multi-type case. So that's the major selling point, which I'll just talk about in the next slide. So the first theorem we show, so we actually give an approximation bound between the multi-agent queue function and the multi-type mean field queue function. Even though Yang et al. Talked about and talked about an approximation, they never really bound the difference in the approximation. They didn't give a bound for the approximation. So we bound this difference between the multi-agent queue function and the multi-type mean field queue function to be less than or equal to 1 by 2 L epsilon, where L is it's a Lipschitz constant with a Lipschitz assumption, and epsilon is the average deviation of all the agent's actions from the mean field. So the other point that I want to make here is that we can show that if the number of agents n is large, so the epsilon actually has an inverse dependence on n. So if the number of agents n is large, epsilon becomes very small, and therefore this approximation error vanishes. So like what I said before, when the number of agents are very large, we can show that the mean field RL approximation errors, all of them go close to zero. So we show two other theoretical results. The first one is just consider an environment which has two types in it, just two types, and let's assume that we just approximate all of them into just a single type. And then if we do that, then the mean action can be bounded by this expression here. And in this expression, we have four terms where K1, K2 denote the number of agents in type 1 and type 2, and N is the total number of agents. And epsilon is the average deviation from the mean field of type 1 and an action of type 1. And epsilon 2 is the average deviation of action of type 2 and the mean field of type 2. And alpha 1 and alpha 2 are the deviations between mean field of type 1 and the overall mean field, and mean field of type 2 and the overall mean field. Now, if in this environment, instead of just considering this environment with two types as a single type, if we just replace it by if we actually consider two different types, then we have another theorem where we show that the bound on the deviation has been lowered. So now the bound on the deviation can just be given by the first two terms. So this is like an intuition that tells us that if you have an environment where you really have different types, then having a multi-type approach will possibly give you a better performance. Then we also extend theoretical results from Yang et al., which showed convergence to the Nash Q. So we also show that the multi-agent Q function can converge to a bounded distance of the Nash Q. And again, this bound will depend on the number of agents and some other terms. And if there are many agents, we can again show that the deviation is zero. So you can get exact convergence. So empirically, when implementing these methods, we actually devise two different scenarios for the multi-type approach. The first scenario is the predefined known types. So you see in some environments, you have a large number of agents, but you already know that some of these agents will belong to a particular team. So all these agents can be classified into teams or groups even before learning takes place. In real world scenarios, typical examples are elections in multi-party democracies, where some of these parties may come together to form a coalition before the election, and the electorate know which coalition they're voting for instead of which party they're voting for. And then you also see such examples in logistical business scenarios, like there are alliances for aircrafts. Popular examples are Star Alliance and the One Way Alliance and so on. So here a bunch of aircraft companies come together to form an alliance. And when you're purchasing a ticket, you know which alliance you are purchasing the ticket from. There are other environments where there are typically no types in the environment in itself. Like if you look at examples of stock trading or examples of some massive multiplayer online games, there are no real types in the environment. But here we again argue that the agents can, if the agents have an intuition for grouping others, they can probably group all the agents virtually into a set of types, and that will make learning in these scenarios tractable. We provide and implement like a practical algorithm for each of these scenarios. First, let me just discuss the implementation practical algorithm for the known type case. So the algorithm follows Amnee's DQN in spirit. So we have two Q networks, the Q eval and Q target network, and then we compute all these different variables that I just talked about: the Q function, the value function, the mean field action, and the policy. In sequence, we calculate all these values and then store the values in an experience replay buffer, and then update the Q functions as in normal practice. So the use of these neural networks helps to scale the methods to large state action spaces. For the unknown type case, the algorithm is very similar to the known type case, except that we have an additional step where we perform k-means on the number of on the actions at every time step. So if every agent has an idea of the number of groups that they want to group the other agents into, they can perform a k-means, and then they can just cluster all the agents into different types based on the k-means result, and then give a best response to these types rather than giving a best response to every other agent. So practically, to demonstrate the usefulness of this approach, we formulated experiments in the Amii testbed. Amii is kind of the standard testbed in mean field many agent learning studies. So we have three games here: multi-team battle, battle gathering, and predator prey. So in each of these games, we have about 4 teams, and in each of these teams, there are about 72 agents. So overall, there is about 220 agents in the environment. So in the first game, which is multi-team battle, you have four teams which are trying to fight against each other. And the team which has the most number of agents alive at the end of the battle, they win the battle. So the team has to cooperate within themselves and compete against other agents from opposing teams and kill opposing teams to win the game. So battle gathering is very similar to multi-team battle, except that the agents also have some additional responsibilities, like they have to capture some food and complete some tasks before for winning the game. And in the predator prey environment, we have 2 different types of agents. Like we have the predators as well as the prey. And then there are 2 teams of predators, and then there are 2 teams of prey. The predators are more stronger, so they look to capture the prey. And the prey is more faster, so they look to escape from the predators. So let me quickly go through the results. So for the training and for the experimentation using the multi-type mean field Q algorithm, we have a 2-stage training process. So we have a 2-stage experimentation process. The first stage is the training process, where we train all these methods for about 2,000 episodes. And after the training is completed, the trained algorithms enter a face-off where they compete against other algorithms, and we plot the results for the face-off as well as the training. So the baselines for us are MFQ and MFAC. Both are mean field RL algorithms released by Yang et al. And then IL, which is an independent Q learning technique. So independent learners have always been proposed as potential algorithm use for the many agent case. So we also compare to the independent methods with IL. And in both the training as well as the testing phase, the MTMFQ algorithm does better than all the other baselines for us. So that one was for the known type case. So every agent knows which team the opponent belongs to. And for the predator-prey, we model that as the unknown type case. So agents don't know what the other opponents belong to, which team the other opponents belong to. So here again, we have the same baselines, and then we show that MTMFQ does better than the three baselines in both the training as well as the testing phases.
Quick clarification question, Sriram.
Sure.
So when you are doing the face-off against other algorithms, am I right that all of the agents on the same team have been trained by the same algorithm?
Yes.
Okay, thanks.
Yeah. Okay, so now, so I talked about relaxing the first assumption. So yeah, before I go forward, any other questions? Any other questions? All right. So now, just I have talked about relaxing the first assumption, which is that the agents are homogeneous. Now I move on to relaxing the second assumption about the observability. For this scenario, we assume that the actual mean field metric is not available, unlike the Yang et al. Paper, which assumed that the environment is fully observable and the mean field metric is readily available. So every agent computes a belief over the mean field action, which we denote as A tilde. And this is a per agent belief. So it's important to understand the key difference between this approach and the mean field RL approach is that every agent has its own belief. The A tilde for agent J would be different from A tilde for agent K, which is different from A bar. A bar is the overall mean field, which will be the same for these two agents if they belong to the same environment. As far as the assumptions are concerned, we retain the first assumption now, and then we relax the second assumption. So we are saying that the environment, let's assume that the environment has just a single type. Let's assume that all the agents are homogeneous, but they are not fully observable anymore. The fully observable property has been relaxed. The Q function now can be approximated using the POMFQ function. So now the major differences, if you see from MF and POMFQ functions, the major differences are that the state is the local state Sj instead of the global state S, and the mean field is the mean field belief A tilde and not the full mean field A bar. So this is the major difference, and we show that you can still approximate this using the POMFQ function. So for the POMF, which is the partially observable mean field Q function, we introduced two different scenarios. We studied two different scenarios for partial observability. The first scenario is the fixed observation radius, or FOR. So here we assume that you have an environment in which an agent is able to partially observe or fully observe all the agents in a fixed neighborhood around it. So there is a fixed neighborhood, and the agents are able to get complete information in that fixed neighborhood. And outside that fixed neighborhood, the agents get zero information. The agents can't see anything. Good examples would be games. Like if you see, if you play large multiplayer online games or any games per se, there is generally this concept of a mini map. A mini map is a small space around an agent, which the agent can see or get complete information from. And outside the mini map, then there's not much information that is available. Then there are some applications in logistics like demand and supply operations, which in the real world, they may not be a fixed observation radius per se, but there have been like lots of previous work which have modeled these scenarios with particular neighborhood constraints. And many of those modeling can also be done using the fixed observation radius part of our analysis. We have the second category, which is the probabilistic distance-based observability. Here we relax the assumption further, and here we say that you can't assume anymore that you get all the information from this fixed neighborhood distance, but the observation will be varying based on several factors. So you could see more or less agents or more or less distances based on several factors like obstacles or like the viewing angle, or an example would be blind spots in autonomous vehicles or driving scenarios. So if there are mirror blind spots, then there are some agents that are nearby that cannot be seen. And but in general, agents nearby can have a higher probability to be seen than agents further away. But again, there are exceptions, because if you have mirror blind spots, then you can't still see agents nearby. Pedestrian motion is another example where when you're modeling pedestrian motion, you see that there are agents which are modeling human behavior as they walk across the street. And typically, you don't get full observation in a particular fixed neighborhood because there are obstacles and there are viewing angles and so on. So I come back to the update equations that I spoke about briefly before. For the MFQ case, the update equations are like just as a recap. The update equations use the scenario uses the full observability. So here you have the green agent, which is a central agent, and we assume that the central agent can see everybody in that neighborhood. So all these red agents are viewable, and therefore the A bar, which is the mean field, is calculated across all the agents for across all the agent actions. Because you assume that everything is just observable. So for us, we have two conditions. We have two different categories. One is the FOR and the other is the PDO. In FOR, we assume that the central agent can only see a small neighborhood around it, and every agent outside this neighborhood is not observable. So all these blue agents are not observable, but all these red agents are observable. And in PDO, again, the agent can see varying number of agents based on different factors. And here, these red agents around the green agent are observable, and the blue agents are not observable. So for both these scenarios, we maintain a Dirichlet distribution because you see the mean field action is a categorical distribution. So the Dirichlet is the conjugate prior of a categorical distribution. So we use Bayesian updates and we make some conjugacy assumptions. And we use the Dirichlet prior, and at every point of time, the Dirichlet is updated based on the different samples that the agent can see. And this Dirichlet distribution is used to obtain the mean field belief action. And that action is used in the Q updates. So for the Q function update equations, if you recall, the Q function was just the Bellman update for the MFQ update. For the POMFQ update, we have a very similar update, except that instead of the fully observable state, we replace that to be a local state, and we replace the fully observable mean field to be the belief over the mean field. And for the PDO, we actually maintain another variable lambda. So because you see in the PDO case, there are more or less agents viewable in a given situation, and the agent gets a mean field, metric, a mean field value, which is the A tilde, but the agent does not know how much to relay or not relay on that value. Because it does not know at a particular point of time, if there is no additional parameter, it does not know at a particular point of time how much information it's getting. So this lambda actually captures the amount of information that it's getting. So it's like it captures the probability of viewing another agent given that agent's distance to the central agent. So that captures the reliability of of the mean field metric in this case. So given that, we have the Boltzmann policy updated similarly to what we discussed before. And the major differences still apply. Instead of the full mean field action, A bar, we have the A tilde for the for updates. And for the PDO updates, we have A tilde as well as lambda bar, where lambda bar was this parameter I just explained in the previous slide. So again, we have two very practical algorithms for each of these different categories, one for FOR and one for PDO. And in spirit, again, it's very similar to DQN, but now we update a Dirichlet distribution, which is being maintained for the A tilde, and we compute the new mean action using the Dirichlet distribution and use that for the updates. For the PDO case, we have all the steps from the FOR case, but in addition, we also have this lambda bar parameter, which is a distance parameter. So we update that using an additional distribution, which was the gamma distribution. So we have two experiments again. We provided a series of experiments in all the same agent test beds as that I discussed before. So in the multi-team battle case, which we formulated two different variants, which is FOR and PDO. So in the FOR case, we have the same agents in the battling against each other to win the battle. But here, the agents can only see a fixed neighborhood around it, which is different from what we had before, where the agents get full observability of the entire environment. We had the same baselines, IL, MFQ, and MFAC. We have the similar training and testing procedure. And the important observation is that FOR does well in both the training as well as testing phases. And the FOR POMFQ algorithm beats the other algorithms more than 50% of times in the testing phase. And in the training phase, it clearly shows a better performance. And in the PDO case, again, we have a similar procedure, but now we also use both the POMFQ PDO as well as the FOR algorithm to see how they perform in this scenario. So here it shows that here the results show that in the training phase, the POMFQ PDO does better than all the other baselines, including the FOR variant. And the major reason is what I explained before, that if there is no additional distance parameter, which is what the FOR algorithm has, the algorithm does not know how much to rely on its own mean field, but having that parameter improves performance in both training as well as the testing phases. Okay, so let me conclude by saying that there were two important contributions that we made to the MFRL literature. One is we extended MFRL to multiple types, which was not possible before. And we also extended MFRL to partial observation of the mean field action, and which will allow mean field reinforcement learning methods to be more widely applicable to a large number of environments. Because this is a very recent technique, there is a large scope for future work. One of the things that we are looking at is to combine these two things that we did, to combine the multiple type approach and the partial observation approach. Extension to continuous action spaces is still an open problem. In mean field reinforcement learning, all the study has been restricted to discrete action spaces, like I mentioned, but there is some scope for extending them to continuous action spaces. There are a lot of real-world applications that are possible for this approach. I think DD and Lyft is using this method for ride sharing, order execution, like optimal order dispatching and execution. So DD Research had a paper on using mean field reinforcement learning for order dispatching in ride sharing applications. So there are applications in smart grid and also some good applications in physics. So Yang et al. Showed a very good application in solving the icing model, which is a popular physics model for calculating the magnetic energy in dipoles, and to calculate the optimal dipole moments in large atomic environments. So there are some other physics models that are also that will also benefit from the mean field reinforcement learning approach. Okay, so I would like to conclude with that. There are some important links to the paper, as well as you know where to find me when you have questions. So thank you for this opportunity, and I'm happy to take questions. Okay, so let me check the chat first.
A bunch of people use the clap emoji, and I don't think there are any questions in the chat, but hopefully someone will be willing to unmute and ask.
Okay. Even if you have feedback, like if there was something that you didn't understand, if you want me to go over it again, or if you had some feedback on our research or the talk itself, I'd be happy to hear that as well.
Yeah, I had a question regarding you had mentioned that you use k-means, so specifically regarding how you come across the types, and like as the agents learn, how does the clustering of types improve throughout? Because you know what I mean, if you don't have the types, then at what point do you converge on like, okay, these are the types we're going to stick with, versus kind of continuously learning the clusters?
Yes, so these are different approaches. So you could look to continuously learn you look to stick to types or continuously learn the different types, and these two are different approaches that works on different environments. So as an example, if you look at stock trading, like you have a bunch of agents which are trading, and then agents, like if an agent wants to just group the other agents into, say, types of risk seeking, risk averse, and risk neutral, this is not really a fixed type per se. this is just a type that an agent came up with because it can tractably solve the problem and hopefully give a better optimal response. But you see, agents can still change their type. They can still change their strategies. They can go from risk seeking to risk neutral. They can go from risk neutral to risk averse based on how the market changes. So in scenarios where there are no real types, we find that having this dynamic type allocation, where at every point of time, the agent is looking at the actions of the opponents and then dynamically classifying them to types, we found that helpful empirically.
Got it. Cool. Thank you.
Mhm. Any other questions?
I'll ask a general question. So you mentioned there's a bunch of future exciting possible work. If you want it, let's say we really want to apply this to firefighting or pick up and drop off for Lyft and Didi. What do you think are the most important things to focus on first? Are there one or two things that really stick out to you as critical that the field needs to improve?
Yes. So looking at the broad picture, we are looking at methods here that improve the scalability of multi-agent reinforcement learning algorithms. And there are, like I said before, there are many different methods that that can do this, and people are approaching this from different angles. Mean field method is a popular way of doing it, but mean field method has these critical assumptions that I talked about, especially those two critical assumptions. So being able to relax these assumptions and being able to apply it in a particular environment that is suitable for this will be critical, because one assumption that you cannot remove from a mean field method is that you need to assume that agents are only maintaining weak interactions through a mean field, and this should be true in the environment. So if you have an environment where you have a bunch of agents all doing different things and you respond to the mean field, and that's highly suboptimal, then probably you can't use the mean field method directly. So in real world examples, it's important for us to understand the environment properly to see what will be the case. In something like in a very dynamic environment like firefighting, I think the first advantage is that the environment is cooperative. So you have a bunch of agents, all of them are cooperating with each other. So per se, the agents are because the agents are cooperating, you can the mean field approaches in cooperative environments generally give a very good performance, more than cooperative competing approaches. So agents can coordinate a little bit, and that will help in maintaining the mean field structure of the environment. But in possibly competing environments like autonomous driving, pick up and drop, where an agent is trying to improve its own revenue and it doesn't particularly care about the other person's revenue, then it could be quite tricky, because an agent can look to improve its revenue and it can look to do something completely adversarial for the other agent. So it is important for us to understand the dynamics of the environment before we can see if it can be applied.
So if people are thinking about using mean field reinforcement learning, then what? So I guess you should consider using MFRL if there are lots and lots of agents. You should consider using MFRL if the assumptions that it typically makes happen to hold in your domain. Are those the two main considerations, or are there other things that people should be thinking of when thinking about is this a good method to consider or not?
With respect to the other limitations or things that hold back mean field RL from being applied to a large number of environments is like reasons that are true for reinforcement learning in general, like issues of explainability, sample complexity. These are issues that are holding back RL, and once this is solved in the RL space, mean field RL will also be able to just catch up. So
cool. Thank you.
Mhm.
think that might have been enough awkward silence. Maybe last call for questions. And while a reminder that there is a sign up in the chat if people would like to chat with Sriram, which I'd recommend. I think we're doing lots of interesting stuff here at Amii that he would enjoy finding out about. And I bet his work in MFRL could be applicable to some of the stuff you're working on. So please do consider signing up with him, and there'll be an email sent out later. Any final questions before we thank our speaker again? Okay. Well, thanks again, Sriram, for coming here and talking about your work. We really appreciate it.
Thank you. Thank you for the opportunity.
Thank you.
Yeah, thanks.
Thanks everyone for joining in. As Matt mentioned, you can sign up in the one-on-one meeting sheet that is shared by Sabina in this chat box, and she'll also email that out soon. So please feel free to get in touch with Sriram. Thanks, Sriram.
Thank you. See you. Bye.
See you.